at the Center for Earth Sciences, and I will be taking the rest of your lectures for this course. And my teaching assistants are Satya, Pratyusha, and Neha. They will be doing the TA sessions. And if you have a specific questions, and I will be joining some of the TA sessions myself, and we can discuss those at that point. If you have a question, please raise your hand. I'll try and get this thing posted on my side window so that if somebody has a question, I can see it. Uh, Ideally, uh, in an online class, it's very difficult to stop for question answering and then revert back to it. If you could keep your questions for the end, I will really appreciate that. However, if it's a pressing one, you think that you can't move forward without understanding this concept, do interrupt me. Okay, so don't worry about that. Now, if I'm sure Professor Ghosh has covered a lot of this aspect of what controls global temperature, stable isotope geochemistry, and everything. So in my part, I'm going to be mostly talking about what sort of role the oceans play in moderating global climate. Okay. Now, in order to understand the role of the oceans, we're going to start with some idea about circulation. What these graphs are showing you are a temperature gradient across north to south. This is North America. We are going from the Gulf of Mexico through the Straits of Cuba and moving northwards by New York, Boston, all the way up to the close to the Arctic Circle. And the darker colors or the warmer colors are showing a movement of really hot water. So essentially, we can see there is a flux of hot water from the equator going towards the pole, okay, which is further manifested in the second plot, which is giving you a preview of the sea surface temperature, which is the first few meters of the surface ocean. And you can see around Florida, it's really warm and things are moving northwards and there are eddies diffusing out. So the question to you is that why do we have movement of air and water on this planet? And all of these movement is for one singular purpose, to, to bring the planet in a thermal equilibrium so that the temperature at the equator and the pole are the same. So the constant movement of mass in the form of air and wind is for one singular purpose, that the planet's internal thermostat is trying to bring it to a constant temperature. Now, when we talk about global temperatures, it's dominantly controlled by incoming solar insolation, which is manifested in the variation in the Earth's orbital motion and the concentration of the greenhouse gases in the atmosphere. You got to understand one thing. As a planet, we are nothing but a piece of rock suspended in vacuum going around a star. So there are two possible ways you can change, the two possible fundamental ways in which you can change the temperature of this piece of rock. Either you can change the amount of radiation this piece of rock is receiving from the star, or you can change the amount of back radiation that is being trapped around this piece of rock through the greenhouse gases around it. Everything else is a feedback mechanism. So the fundamental mechanisms are either the change in the orbital motion or the change in the carbon dioxide concentration or greenhouse gas concentration around the planet. What I would like to show you is the, um, whoever it is, can you please mute yourself? Thank you. What I would like to show you is why are we bothered about this carbon dioxide in the atmosphere? In the recent past, we have all heard about global warming, but this is one of the key compilation done by NASA, which shows how bad the entire situation is. We are moving from 1950s to around 2014, and these are all instrumental measurements. So we know that these are real data. As we are getting warmer and warmer, around 2 degrees Celsius warmer in the Arctic and a bit less around the equator, we can expect the climate changing, the circulation pattern changing, the freshwater fluxes changing. So it is imperative to understand what's happening to the globe. Now, another key point here is most of the carbon dioxide that has been emitted through industrial burning of fossil fuel, only 60% of it is in the atmosphere. The rest 40% has been taken up by the ocean, because carbon dioxide is, after all, a reactive gas. And in the process, the oceans have become acidic. So we will also cover that bit in the later part of the lecture. Now, to understand what causes this sort of flow of wind or flow of water mass from the equator towards the pole, we're going to start with the energy budget of the planet. Okay. Now, you must be familiar with this picture. There are two possible sources of what should I call it? Heat to the planet Earth. One is the incoming solar radiation from the sun, and the other bit is the internal heat, which is mostly from the decay of the radioactive elements present in the mantle and the core. Now, the internal heat is almost 43 terawatts, whereas the external heat is around 180,000 terawatts. So for all practical purposes, when we are talking about climate of the planet, we're going to ignore the internal heat because it has nothing to do with the heat budget of the surface of the planet. Okay, it has a lot to do with the circulation of material along mantle, degassing of CO2 from the mantle, but nothing to do with the superficial heat budget. Okay, so keep that in mind. Now, you guys are very familiar with black body radiation. We consider the sun to be an almost perfect black body. If we superimpose the sun's radiation given in the red on top of the black body radiation of a black body at 5,780 Kelvin, you can see how well the emission pattern matches with one another. And as we know that the total energy radiated per unit surface area of a black body, when considered across all possible wavelengths per unit time, can be given as a function of its temperature raised to the power 4. Okay, so that brings us to the idea of solar constant. The solar constant is the average amount of radiation received at the top of the atmosphere. We don't calculate solar constant at the surface of the planet because the atmosphere can absorb, trap radiation. That's why when we consider solar radiation, we take the surface of the atmosphere, and the average amount of solar radiation received at the top of the atmosphere is solar constant, and which has to be across a unit area. Otherwise, it wouldn't mean anything. Okay, because we will see that different latitudes will have different amount of energy coming in. Okay, and when the distance between the sun and the earth at its mean, and we also call it the one astronomical unit, the mean distance between the earth and the sun. Okay, so if we utilize Stefan-Boltzmann law, we can say that the flux of the energy leaving the sun is the net power radiated by radiating area, which is sigma T to the power 4, okay, in watts per meter square. And these are the constant that's being used. Okay, now the amount of energy that reaches a planet from a source of energy, which is at a distance r, can be calculated through the inverse square law. Okay, if we are at the source of the energy S and at a distance, say r, we know that the total energy is going to be distributed over 4 pi r square. So the intensity over across any unit area I will be given by S by 4 pi r square. If you double the distance, that intensity will be 1/4, simply because r is in the denominator, r square, and it's a square term. R to 2r, you are dividing the system by 4. So the net power radiated by the sun, we know, is around 3.95 10 to the power 26 watts. And the flux of energy reaching 1 astronomical unit, that is the distance, the mean distance between the sun and the earth, is given by the solar constant S0, which will be 4 pi r square sigma T to the power 4 divided by 4 pi r square, where r here stands for the distance between earth and the sun, and this r is the radius of the sun. So the total area solar constant we can calculate to be 1367 watts per meter square. Okay. Now, this is what is controlling the Earth's annual heat budget. Okay. Now, that is the amount of energy that is coming in per meter square. And if we put Earth as a cross section, a circular cross section in the path of that radiation, we know the amount of energy we're going to absorb is going to be dictated by the surface area of the planet. So the cross-sectional surface area is going to determine how much energy we will absorb. So the area of interception is pi r square, where r is the radius of Earth, and the intercepted solar radiation will be S0, where S0 is the solar constant, and pi r square watts. That's the total amount of energy that is coming into the place. However, there is a caveat to it. The caveat is the albedo. Albedo means the reflectivity of the planet. When we look at absorbed solar radiation, it's actually S0 pi r square 1 minus A, where A is the albedo. Any white surface reflects light, any black surface absorbs light. We already know that during a hot summer day, a sunny summer day, a black car is way hotter than a white car. Okay, so the albedo effect is kind of quantified. Albedo equals to 0 for a perfect black body that absorbs all radiation, and albedo equals to 1 for a perfect white body that reflects all incident radiation. Okay, except for Vantablack, we don't know of anything that is a perfect black body kind of situation. Okay, now Earth's average albedo is around 0.3. Okay, we know that the polar ice caps will have a very high albedo. It will reflect a lot of sunlight, whereas the equatorial blue ocean will have a very low albedo. It will absorb a lot of sunlight. Now, this is a schematic representation of how the albedo looks like across the, what you call it, the latitude. Okay, at equator, we have 0 latitude, we have mostly forest. And as we move towards the south, that's to the left, and to the north, that's to the right, we can see that the albedo is going up because ice coverage is going up. And for all practical purposes, you can take the planetary albedo as 0.3. Now, from that perspective, we can say that the amount of energy radiating or radiated per area is sigma t to the power 4. And the radiation is happening across an area of 4 pi r square. Okay. And so we have to take a step back. Let's look at the incoming solar radiation, which is S0 pi r square 1 minus A. Now, all this radiation that we have received have to be emitted back from the system. The emission has to happen from the planet Earth. We are receiving around 180,000 watts of energy per year, and that has to be back radiated to the outer space for thermal equilibrium to be maintained. In has to be equal to out. Otherwise, the temperature of the planet has to be going up constantly, right? So if the Earth is at a temperature of T, then the back radiation is happening with a characteristic frequency of sigma to the power 4. And radiation is happening across an area of 4 pi r square. So the total emitted radiation is 4 pi r square times sigma t to the power 4. Okay, and this is for the fact that Earth is in thermal equilibrium. Temperature is not changing with time. Okay, if there is a change in temperature with time, this equation doesn't hold true. So that if there is an increase in temperature, we have to say that the amount of radiation received has to be greater than emitted. If there's a decrease, then the rate of emission has to be higher than the rate of absorption. Now, we know that the incoming solar radiation is S0 pi r square 1 minus A, whereas the outgoing is 4 pi r square sigma t to the power 4. Then we can calculate the average temperature of the Earth to be around 255 Kelvin or minus 18 degrees Celsius. But in reality, the global average temperature is around 288 Kelvin or 15 degrees Celsius. So there is around a 33 degrees Celsius change in temperature between what we can calculate some simple thermodynamics versus what we observe through instrumental measurement. This is simply because of the greenhouse trapping of the back radiation. And we have already know that for any black body, for Wien's law, we know that the lambda max can be given by the equation that lambda max equals to 2,897 micrometers Kelvin divided by the temperature of the black body in Kelvin. For Sun, the temperature is around 5,777 Kelvin. For Earth, with greenhouse effect, it's 288 Kelvin. So the lambda max for Sun lies around 0.48 micrometer. whereas for Earth it lies around 10 micrometers, which is in the IR spectrum. For the Sun, it's in the visible spectrum. And this is how we represent that. The Sun is to the left, the Earth is to the right, and for the Earth, we are taking the mean annual temperature to be devoid of any greenhouse cover, which is 255 Kelvin. And the incoming visible radiation comes through the atmosphere, but the back radiation in the IR wavelength is being absorbed by the greenhouse gases. Among the greenhouse gases, the more important greenhouse gases are carbon dioxide, methane, and water vapor. Water vapor concentration of the atmosphere is variable, which varies as a function of its relative humidity. Now, why is CO2 and water vapor so important? Any molecule which has a dipole moment, okay, which has to be IR active. CO2 in its normal vibrational mode doesn't have a net dipole moment. However, water has a net dipole moment. So water in all possible vibrational mode should be IR active, whereas CO2 is not. If we look at CO2, the symmetric stretch of CO2 doesn't lead to any change in dipole moment. So it doesn't absorb any infrared radiation in that particular stretch oscillation mode. However, the asymmetric stretch and the oscillations, the wobbles, will also lead to change in its dipole moment and will lead to a absorption in the IR band. So CO2 plays an important role in jacking up the temperature of the planet from 255 Kelvin to around 287 or 290 Kelvin. Okay, this is all that is it to it. Okay, I think you guys are very familiar with it. But what I want to introduce to you is that of all the greenhouse gases, anybody has a question? Of all the greenhouse gases like CO2, methane, nitrous oxide, CFC, they have very different global warming potential for 100-year time horizon. And they have very different atmospheric lifespan. Why do we normalize everything to CO2? Why do we go gaga over CO2 in terms of a global greenhouse gas? Because it has a pretty long atmospheric lifetime. And its concentration in the atmosphere is much higher than any one of these other greenhouse gases. So keep that in mind. Okay, so we will revisit the bit that is controlled by this Earth's orbital motion around the Sun in terms of controlling its temperature. Now, there are three parameters in Earth's orbital motion around the Sun. The first is the shape of the orbit around the Sun, which is given by the eccentricity. It can either be circular or it can be elliptical. Second part is the axial precession, which is the change in the wobble of the planet around its own axis. And the third part is the obliquity, which is the change in the angle to which it's tilted. Okay, so there are three particular parameters in orbital motion we have to be cognizant of. Now let's first start with eccentricity. The eccentricity is nothing but change in the ellipticity of the Earth's orbit around the Sun. Now that the shape varies between an ellipticity of 0.0034 to 0.058, which is slightly elliptical. And 0.0034, an e-value of 0.0034 is almost as good as circular. And this change happens over 100,000-year time scales. Okay, why are we mentioning these time scales? Because these time scales will become important when we are trying to understand glacial, interglacial climate change. Okay, now what is the consequence of that? Let's do a quick recap. We know from inverse square law that the amount of energy that we receive is around 1367 watts per meter square, right? Now, if the Earth's orbit was a perfectly circular system, we won't have a change in the solar radiation between January and July. Now, solar constant, as we know, is sigma to the power 4 R0 by R, where if we go back, R0 stands for the radius of the Sun and R stands for the distance between the Earth and the Sun. Okay. Now the Sun's temperature and the size is not varying much over time. Okay. Has it varied over the last millions and billions of years? Definitely it has. But for our time scales, which is between tens and hundreds and thousands of years, it is not varying by much. However, if the Earth's orbit around the sun was circular, we won't have any seasonal difference in temperature. It will just remain flat. Okay, that is this eccentricity which leads to the change in temperature. Why is it happening? We can look at it from the perspective of time going from 0 to 365, that is across a year, and the distance from the sun in millions of kilometers. We have perihelion, where we are the closest, and the aphelion. Okay. Now, when you are at the furthest away from the sun, the amount of energy received will obviously be a bit lower, because the R value, the distance between the sun and the earth is increasing, and we know the S0 is a function of this R. Okay, so moving forward, if we calculate the amount of radiation we receive in watt per meter square, then we can see that at perihelion we have an energy received around 353 watts per meter square, whereas in aphelion we have a energy received around 332 watts per meter square. So there is already a seasonal bias in the energy that we received between January and July. Okay. Now, does that remain constant over time? We know with time the eccentricity of the orbit is changing, right? For an eccentricity value of 0.005 given in blue, which is an almost circular orbit, if we do the same calculation, time going from left to right, 365 days, an insolation in watts per meter square, we have perihelion in this part and aphelion in this part. We can see for a quasi-circular orbit, there is not much of a difference in incoming solar radiation between perihelion and aphelion. Okay. However, as the eccentricity increases, the seasonal contrast in the amount of energy received is going up. So remember, there is a seasonal contrast in the amount of energy received as a function of the ellipticity of the orbit. Okay, and that can be summarized in the annual average insolation, that is watts per meter square, over the eccentricity like this. As the eccentricity is increasing, the annual average insolation is changing. So keep that in mind. That is the effect of eccentricity that we have. Okay, this is the shape of the orbit. Next comes the latitudinal distribution due to axial precession. What is it? The axial precession is its movement, rotational movement around its axis. Okay. Now, axial precession has a typically rhythm of around 23,000 years. The axial precession is essentially controlling the seasonal contrast of temperature due to a particular eccentricity. If an eccentricity value is low, there will be no seasonal contrast with the precessional cycle. However, if the eccentricity is high, we can expect a large seasonal contrast with the precessional cycle. So we're going to kind of ignore the precessional cycle for now, because this will become important when we talk about glacial interglacial cycles. But for the heat budget of the planet, on an annual basis, on a decadal basis, the precessional cycle has very little to do. Okay. Last but not the least is the change in obliquity, which is the tilt of the axis from its mean value. And it's ranging between 22.1 degree to 24.5 degrees. And this tilt controls the latitudinal distribution of solar radiation. Keep in mind, the eccentricity was controlling the annual or the seasonal distribution of solar radiation. This is the seasonal distribution of solar radiation, whereas the obliquity is controlling the latitudinal distribution in solar radiation. How do we get to that? It's quite simple. We have done it in high school classes. Around the equator, we have perpendicular radiation at higher latitudes. The radiation is at a much lower angle. And it's the same amount of energy distributed over a small surface area versus distributed over a large surface area. Okay. So if we look at it mathematically, the intercepted radiation is solar constant times pi r square, which is 1370 times pi r square watt. okay, which is around 342 watts per meter square. That is the average. But if you calculate it across the latitude, you'll see that at low latitudes, you have a much higher amount of radiation received. At high latitude, you have a much lower amount of radiation received. Okay, which can be translated into a picture like this, where we are going from January to December, and we are looking at the latitudinal insolation in watts per meter square, given around the y-axis, from 0 degrees, that is the equator, 30 degrees north, 60 degrees north to 90 degrees north. Okay, to blow it up, this is what it looks like. We are going from 0 to 360, January to end of December. If we look at the equator, which is given in red, we don't see much of a seasonal contrast in the insolation in watts per meter square. And then if we move to around, say, Tropic of Cancer, there is a slight seasonal contrast between the winter and the summer months. However, as we move further north, as we get to the Arctic Circle and the North Pole, we can see that around 60 degrees north, which is the Arctic Circle, there's a large seasonal contrast between incoming solar radiation between summer months and winter months. Okay, keep that in mind. So there is a latitudinal variation in incoming solar radiation, which is leading to an energy imbalance of the planet, right? Now, this solar radiation, this is a calculation of the incoming solar radiation given in watts per meter square over number of days of the year for different tilts. We are looking at tilts of 22.1 to 24.5. So with the change in the tilt, we have not much of a difference in the incoming solar radiation. We are going from around 470 to around 520. That's a 50 watts per meter square change in incoming solar radiation. Now, what does that difference lead to? If we look at the energy imbalance of the planet, okay, what are we looking at here? We are looking at latitude going from 90 degrees north to 90 degrees south, and we are looking at radiation intensity, okay? The red line is your shortwave solar radiation, okay, insolation. The green line is your long wave terrestrial back radiation. The area in dark blue is where we have energy surplus. The area in light blue where we have energy deficit. So essentially the green line is the radiation intensity of the planet. If the planet was a perfect black body, if every part of the planet was at the same temperature, the green line will run parallel to the x-axis. However, it is not, because we know that the poles are much cooler than the equator. So the green line itself has a shape, whereas the red line is the incoming solar radiation. What we can see around 35 degrees north and 35 degrees south, that the incoming solar radiation and the outgoing solar radiation are equal to each other. Between these two latitudes, there is a net excess in the energy that we receive. And beyond these latitudes, there is a net deficit in the amount of energy we emit. So the globe is constantly trying to move energy from this surplus to this deficit. So there is a constant movement of material, whether in the form of wind or whether in the form of water, from this energy surplus to this energy deficit zones. Okay? The first and foremost of which is the movement of wind. Along the equator, you have an energy surplus. Okay? The incoming radiation is heating up the air. Air leads to thermal expansion, lower density, it will rise above. As it rises above, it can move towards the pole. Why? Because at the pole, at a lower temperature, density is increasing, thus it's dropping from the top of the atmosphere to the surface of the planet, and we are starting a convection cell where at the equator you are making things warm and making them rise, whereas at the pole you are making things cold and making them sink. So in an ideal planet which is not rotating, okay, the key factor is a non-rotating planet, which is perpendicular to its axis and moving around the star in a very circular pattern. This is the kind of wind circulation we will expect. Two cells starting from the equator, going all the way towards the pole, okay, and movement of air along the surface of the planet from the pole towards the equator, whereas movement of air from the equator towards the pole at the top of the atmosphere, okay. So there is cold wind coming down the surface of the planet and warm wind moving from the equator towards the pole along the top of the atmosphere. However, that is quite difficult to achieve. Why? Let's take a view of the planet from the equator towards the pole. Okay, we are taking a top view of the planet. At the equator, this is your circumference. Say around 30 degrees north, this is your circumference. If you take all the air mass around the equator and try and squeeze it towards the 30-degree north, the total volume of space available to you is shrinking, right? And this shrink causes a change in density because you're packing more and more air into a smaller and smaller space. So we cannot expect a perfect circulation pattern even if we have an ideal planet which is not rotating, okay? So what do we observe in our planet which is rotating at a speed, okay, and has large seasonal contrast in temperature, and also there is a contrast in the position of land mass at different latitudes. We do observe that at the equator, air gets heated up, rises to a higher altitude, and this air mass, when it moves northwards, it has to sink around 30 degrees north and giving rise to the Hadley circulation cell. Keep in mind, this is known as the Hadley cell. The one above it is known as the Ferrel cell, and the one top of it is known as the polar cell. Okay. Now, the movement of air mass is never perpendicular to the axis of the planet. Why is that happening? Because at the equator, you have an angular momentum. The equator is spinning way faster than anything which is at a higher latitude, because every point on the globe has to go 360 degrees for 24 hours. As the radius changes, as the radius decreases in size, okay, the speed with which the planet is rotating also changes, okay. At the equator, your speed with which you're rotating is the maximum. At the pole, it's the minimum. It's zero. At the equator, it's maximum. So conservation of angular momentum dictates as you move towards the pole, you need to accelerate. So if you take an air parcel from the equator all the way to the pole, it will reach an incredible velocity. So that's not possible. So what happens is that these air circulation patterns are broken up into smaller cells. The first one is the Hadley cell, the next one is the Ferrel cell, the last one is the polar cell, okay? And what we can see is that the movement of air mass along the surface of the planet is not parallel to the latitudinal axes. Why is that happening? This is because of the Coriolis effect. What is Coriolis effect? Coriolis effect is the deflection of any parcel of air or water when it's moving north. Say in the northern hemisphere, when it's moving north, it will be deflected to the right. In the northern hemisphere, when it's moving south, it will also be deflected to the right. Whereas in the southern hemisphere, when it's moving towards the pole, it's going to be deflected to the left from the perspective of this. And it's moving away, it's going to be also deflected to the left. So why does this happen? A particle at the equator is moving very fast towards the right, whereas a particle over here is moving a bit slower compared to the particle, same particle at the equator. If you move the particle towards the pole, what happens is that the planet is rotating at a particular speed, and each latitude has its own speed, whereas the particle has its speed conserved from the equator. So it's going to have an apparent deflection to the right, okay? And that leads to this sort of circulation pattern that we observe in the planet at the moment. So the Hadley cell, where you have air mass moving from around 30 degrees north to the equator along the surface of the planet. At the equator, it rises to the top of the atmosphere, and then it moves towards 30 degrees north. The movement of air from 30 degrees north to the equator has a northeast direction. So the wind is originating from the northeast direction and flowing towards the southwest direction. In case of wind, when there is a direction given before the name of the wind, it is coming from that direction. It's not going in that direction. The northeast wind means the wind is coming from northeast direction. And that is as expected because we are in the northern hemisphere. The direction in which the wind is traveling is from north to south. It has to be deflected to the right, and that is what we observe. Thus, we observe a northwest direction from which the wind comes. So these Hadley-Ferrel circulation cells are not running parallel to the latitudinal axis. They are running at an angle to the latitudinal axis. Okay. Now, this leads to the idea that there is the Ekman spiral. I'm not going to get deep into the Ekman spiral. I'm going to give you a brief overview of what is Ekman spiral. Ekman spiral is whenever we have a wind flowing in a particular direction, the deflection of the water mass right below that wind, the surface water mass is going to be at an angle of 45 degrees to the wind, and that 45 degrees will be to the right in the northern hemisphere and left in the southern hemisphere. Okay. And the net water mass movement, because that subsequent layer of water mass which is moving at 45 degrees to the wind is going to drag the next layer of water mass with itself, and that deflection will be at another 45 degrees, and the layer below that will be dragging it at another 45 degrees. However, with every subsequent layer, the magnitude of the vector is going to become smaller and smaller and smaller. The net water mass movement usually happens perpendicular to the direction of the wind, and it has a huge consequence in terms of how climate works, how ocean productivity works, and what controls global temperature. Okay, the fact that in the northern hemisphere, water mass moves at a 90-degree angle away from the wind direction, and in the southern hemisphere, it moves to the left, and in the northern hemisphere, it moves to the right. What is the consequence of it? The consequence of it is Ekman transport. Ekman transport is whenever you have water mass coming from north to south in the northern hemisphere, we know that my apologies, whenever you have air mass coming from north to south in the northern hemisphere, we know that the water mass will be deflected to the right of that air mass. So if I have a longshore current in the northern hemisphere coming from north to south, the water from the coastline will be deflected away from the coastline, and to maintain a same level of water, because water wants to maintain the same level, surface potential has to be the same, there has to be water coming up from the bottom. Okay, whereas if the water moves from south to north, the water is deflected towards the right, that is towards the shoreline. Thus, there is no change in the water movement. There is no upwelling or movement of water from the deep to the surface. So remember that Ekman transport leads to upwelling of deep waters from the bottom of the ocean to the surface. Okay? And the consequence of the entire wind pattern that we observe on the planet leads to this sort of a circulation pattern in the ocean. Okay. In the next lecture, we want to go deep into why the ocean circulation pattern looks like this. Why do we have formation of deep waters in particular parts of the ocean, and why do we have formation of upwelling of water in particular parts of the ocean? Some of these upwelling will be driven by wind, and some of the upwelling will be driven by simple density. Okay, I'm going to end the lecture right here. I'm going to upload the, slides soon. But before we do that, if you have any questions, now is the time to ask. You can raise your hand and I can call you by name for the questions. Anubhav, go ahead.
Yes, so in one of the slides you showed us the different cells. I think it was slide number 43.
This one or this one?
Yeah, that one works.
Yeah,
Uh,
sure. Go ahead.
so you said that these cycles are broken down,
Yes.
but I don't understand why the directions are, you know, getting opposite for.
Why the directions are getting opposite? For the first, the two end members are dictating the direction. One end member is the equator, the other end member is the pole, right? At the equator, the air has to rise above. At the pole, the air has to sink, right? We can't change these two uh, extreme circulation style. Agreed?
Yes, sir.
And from this particular aspect, we know that when air moves from the equator towards polewards, by the time it reaches 30 degrees north, it has been compressed so much that its density is higher than the underlying layer, so it will sink. And that is what we observe in this particular circulation pattern. By the time it's approaching 30 degrees north, it starts sinking. And one of the key consequences of that is this is known as the Hauss latitude. Any idea why this is called the Hauss latitudes?
I think it was this the time during European when they couldn't. I think I don't know the Europeans they tried sailing across, and
Yeah.
then they couldn't. After that time, the wind wasn't strong enough to push them across. So
Precisely.
they had a lot of horses, and they just decided to unload them from the ship into the
To
sea.
make the ship lighter, or sometimes they would use the horses to, it's like a treadmill kind of system. They have also tried that. So mostly they're going to throw the horses off the ship because to make the ship lighter. So this is the dry region of the planet. All the major dry zones of the planet are located around 30 degrees north. From Sahara to Death Valley, from Taklamakan to Thar, they're all around the 30 degrees north and 30 degrees south. Because here the two air masses sync. We know, and keep in mind, these circulation patterns have a very strong seasonal bias to this. The polar cell is extending up to 60 degrees north in this picture. During northern hemisphere winter, the polar cell can come down to around 40 degrees north. Okay, it will squeeze the Ferrel cell, and sometimes the Ferrel cell can even disappear. Okay, this is an ideal situation of what to expect in terms of heat budget, in terms of density change due to movement northwards, and conservation of angular momentum. Okay,
Yes, sir. Thank you. That makes sense.
yeah, Niloy?
So my doubt is on slide 44.
Sure.
Um, I'm still slightly confused. Why would the surface current be at an angle to the wind current? Shouldn't it be along the direction? I mean, that's
Yes, this is also Coriolis effect, right? Uh, I'm not going to elaborate the Ekman spiral because this is going to be one of your uh, problem set. Okay, this is where I
okay.
would ask you guys to do some research on the Ekman spiral. I'm just giving an overview of the Ekman spiral, saying that every subsequent layer is deflected to 45 degrees. Okay, and during your TA session, you will be discussing this a bit more, and then a problem set will be on the Ekman spiral. Okay.
Okay.
Sir, is there any recommended reading for this course?
I'm going through it. I will upload some. Okay.
Okay.
Anybody has a question? If no one has a question, can we stop here?
And so, have you decided anything about the evaluation of this course? How it's going to be evaluated? Yeah.
We for UG sections we have to go for exams. Like there is no other way we can do it. Are you guys at home or are you guys back on campus?
We are at home.
At home.
Ah, okay. Um, I will discuss with the other instructor and come up with a plan. Okay. We will have to be systematic about what we decide because we can't take classroom type exams. Maybe a take home type exam will be one what we'll have to do. Okay.
So you were saying something about a problem set.
Yes, problem sets will be given during the TA sessions, and we will be graded definitely based on the problem sets. Okay, but at the end of the term, we'll have to do an exam with a bit of margin to it, right? We can't give 100% weightage to the exam. We will give a smaller weightage to the exam, but there has to be some sort of a final exam.
So the problem sets are like also like a take home assignment that we submit like in a day or a week. That's how it works.
The TAs have the authority on it. I think they will do it a weekly basis.
Okay, thank you.
Yeah. No questions, clarifications? And also from the previous lectures, is there any particular point that you want me to brush up or cover? You are encouraged to speak up in my class. There is no problem with saying anything. Okay. If there are any particular sections that you want me to cover from the previous section, just let me know. Okay. If there is nothing else to discuss, may I conclude the class here?
So one more thing, the
Sure.
recorded lectures, can you please upload them to Microsoft Stream or else, and also put them in the lectures tab so that people not everybody needs to download them and rewatch or anything.
Microsoft Stream.
Yes,
Well,
putting them will help us.
I'm technologically challenged, so I will ask the rest of the group to take care of that. Okay, don't worry. Okay.
So can we sir download it and upload it in Microsoft Stream by any of our student group
Yeah, you can do
Or
that.
we could download it and put it into our own YouTube. We'll make an unlisted YouTube. If
Sure.
we're not able to do a Microsoft Stream thing, we can make an unlisted YouTube playlist and do it. We have done it for other lectures, so we can do it here as well if you want.
That's no problem. I have no problem with that. Okay.
Okay.
Okay. Thank you. Okay, dokes. Bye-bye. I'll see you guys. 25th is the next class, right? Let's take a call on it soon. Okay. I'll see you guys either on Friday or next week. Okay? Bye.